I just ate, so I'm kind of like...
Oh no, it's hindering. So since
Alright guys, let me catch up to you. So that's what I got. Is that what you guys got?
Yeah.
So what's the slope?
I did something.
You did something, alright.
But it's only up by a little bit. 0.001.
Is that what the same numbers you guys got?
Yeah.
So 11, so the slope is what? Yeah, so 1140.4 roughly. And the y-intercept is that 17,600 and basically 50 cents. So if I had a state, according to this line of best fit, if I had a state that had 0% of the people have a bachelor's or higher, I would expect the median income to be $17,600.50. Don't forget my 50 cents. You guys with me? Yes? No? Not at all? Why do I trust this line? Because what's our R value? 0.808, basically. So in order to show any correlation at all, and I'm always going to give you this number. I showed you the other day that it comes out of a table. Sort of related to a Z table and a T table, all that kind of stuff. It's an R table. And this is sort of like saying Z star has to be bigger than 1.645. It's the same idea, right? So I'm going to give you this number. So if we got an R value of 0.49, there's evidence of correlation, but I would say it's really weak because it just barely got over the threshold. If I got R of 0.47, not enough evidence to show any correlation at all, I wouldn't trust the line. Alright, so we're definitely going to trust this line because we blew that test out of the water, right? We had to get a 48 to pass, and we got an 81 almost. So we passed that sucker. You guys understanding what's happening? Okay. So, interpret R. Tell me a couple things about it. There's two things I definitely need to hear from you about it. The first one's almost too obvious. Okay, it's strong, or moderately strong, that's cool. Moderately strong. And it's positive. Meaning as one increases, the other one also increases. Alright, again, I like that sound too. Alright, what does this tell us about the line of best fit? And I pretty much gave it away a second ago about what I was saying about the line of best fit. Do I trust the line of best fit?
Yes.
Yes, I do. I totally do. It's a strong correlation. Even if I got 0.49, I would still use the line of best fit. If I got 0.47, I wouldn't. But how much do I trust the line of best fit? I trust it pretty well. In fact, so what does it tell us the line of best fit? I trust it to make predictions. I trust it to make predictions. So then the next thing I ask you is make a freaking prediction. Go away. So one thing you guys had to figure out was where to put that exactly. 34.6% is which variable? X. Because you put this in list 1 and this in list 2. XY table. Oh my God. So if you make X point, yeah, that point, 34.6. Or, as you saw the other day, you could just hit second trace to get to calculate value and just put it in. The calculator's got the line in there. Hopefully you put it in there. So here is, did I put it in there? Not yet. Probably. No, Jeff. This is exciting. How do you use this thing? Dadgummit. Sweet. Alright, so this is what you got to come up to show me on the day of the test. Or the quiz. You gotta show me. Show me.
I appreciate it.
So I could just plug it in and put it in the calculator like normal, or I could just go second, trace to calculate value, and just put in 34.6 and let the calculator do it for me. Either way you do it, you get $57,058.34. Roughly. Well, again, it depends on what you put in there. I put in there 1140.4 and 17,600.5. If you rounded more or less, you'll get it slightly different. What matters is it's around 57,000. Now, why did I say compared to Virginia? Because Virginia has 34.6%. So we predicted that the state would have $57,000 income, median income, and they actually have a $55,000. That's pretty close. Now, I knew it wasn't going to be perfect. How did I already know it wasn't going to be perfect? Because R is not 1. But R is 0.8. It's pretty good. It should be pretty close for most of the data points. How are we doing so far? I mean, is this all right? I mean, compared to some of the stuff we've done in this class, it should be not too bad. Finally, this weird-ass question. Your results mean that if you get more people at stake that earn a master's degree, then the median income will increase. For sure. No, it does not mean that. Does it mean that it won't increase? No, you can't say. All you know is that they seem to be related to each other. There are other factors that affect both things, and they might not affect each other directly. They might just be both affected by different... I can't say. All I can say is that my data has a connection between those two data points. There's a connection. There's no causation. I can't say anything about what causes the other thing. Maybe if people earn more money, they have enough money to go to college, right? Maybe it's the other way. Maybe it's both ways. Or maybe there's a third thing. I don't know. Shit. Yes. And this goes along with the whole theme of statistics being the most honest math there is. It says it looks like this could be some kind of connection, but what it is, I can't say yet. We've got to do more study if I want to see deeper into it. All right. So how do you guys feel about that? That should be definitely not too bad. You just got to remember how to use a calculator on the day of the test. You'll be all right. Okay. So, if there's no questions on that, yes?
For the last one, do we just answer it in words, or do you have to...
Yeah, you just say... Your results mean that if you get more... No, you can't say. The greatest thing to say to this question is correlation does not imply causation. Now, normally students consider math to be like settled. Most of the math you learn was set up like several centuries ago. Are you with me? Statistics, there's a lot of controversy. There's movements to make it go in one direction or another. None of those controversies really changed this level of stats much. But there's this big thing about being careful. Now, correlation does not imply causation. Does that mean that bachelor's degree, having a higher bachelor's degree wouldn't cause income? No, I can't say. I just can't say. Some teachers are saying, no, it's not. If you did, it wouldn't. No. I mean, you just can't say. Maybe it does. What kind of a test would I have to do then to see that? I would have to take a state, actually increase, and then see what happens. I'd actually have to go through the whole experiment and see what happens while controlling other variables. That would be a remarkably difficult thing to do. I can't control all the variables that affect this, like the general economy, right? What's going to happen? I don't know.
Just going to ask, when would you say yes to the question like that?
The funny thing is, for this problem, you would never say yes. I don't even care if it seems to make sense, right? But still, from what we've done, we can't say. This study does not address that question, which is really the point I'm trying to make. The study we've done does not address this question at all. It just says that they seem to go together. Why? The study doesn't say. But since I see a relationship, maybe I'll do a study that will actually look at that question. If I see something that's not related at all, I'm not going to waste my time.
It was like a science experiment then, you would maybe say it?
Yeah. So this is what's called exploratory statistics, where you just go out and you start seeing where's there a connection. And there's a connection, so maybe now we'll set up some experiments and see what's happening. If it's possible or ethical, right? Obviously, there's a lot of things that wouldn't be ethical. You want to go to college? No, you're in the control group. Stay home. Stop it. I want to see what happens to your income. No, it's probably not ethical. All right, how are you? All right. Any other questions on that kind of stuff? Now, I know there's a lot of sections in chapter 11, but they break it up so much. We basically, everything we just did is all of chapter 11. I'm sorry, 12. Chapter 12. The correlation chapter. We're about to go back to chapter 11 right now. We haven't started that yet. Okay. So here's some good news for you. In chapter 11, we're going to do 11:1 and 11:2, and that's it.
Oh my God.
Yes, I mean, yes. All right. Now, chapter 11 is a weird chapter, but once you get over the fact that we're going to deal with a different distribution, we're going to have, oh yes, another chart. Statistics, the math of charts. At least if you take it with me. Old school Jeff. But I want you to understand, can you draw right now for me a normal distribution? Just draw it. If I make it a standard normal distribution, what is that? Standard normal distribution. Standard. Where's the G coming from, Jeff? Yeah. What's up, G? Standard G. The G standard. All right. Standard normal distribution. So, I mean, all of you can just do this, hopefully. Or something like that. Maybe a triangle. I had a person that had to do a triangle. Great. What's going to be in the middle, though, if it's a standard normal? 0. Beautiful. Standard normal means I've made it into z-scores. So I could have a normal distribution. Its mean could be anything. But when I make it into a standard normal, it's 0 and it's got 1 and -1. It's the standard normal that follows the chart that we have, the z-score chart. Are you guys all with me? Now, how do I get from like a normal distribution where the mean could be anything to there? Well, I could use this formula, right? Or I could use this formula. Oh shit, right? Or I could use this formula. Don't write all that crap down. But, I mean, don't these look vaguely familiar? All of these do the same thing. They take the picture as it is with x's, raw score x's, raw percentages, raw sample means, and it converts it into a standard normal. This guy exists already, just sits there existing. And it's described by your z-scored chart. There's a purpose to all this, by the way. It's not just a good review, it's going into today's lesson. Okay, so there exists something called a, oh, you're going to like this, something called a chi-squared distribution. And, yeah, it looks like an X. It's like the Greek letter X. And that's why it's Kai. Not the guy from Dragon Ball. No? Yes? A few of you? Okay. You're like, what is he talking about? Don't worry about it. Alright, how are we doing so far? And this picture changes a little bit based on how large my sample is. And we've seen that kind of thing already. Not with the Z, but with the T. Doesn't the T change a little bit depending on my sample size? Oh, you guys remember that. Because the chart changes according to the degrees of freedom. The numbers change. That means that the distribution changes based on that. So what this is, one thing I don't want to get, we don't have enough time to get too deep into the math behind this, but it's sort of like folding the normal distribution over on itself, which is kind of neat. And it definitely starts at 0 and it goes this way. And one thing this is used for is for plotting standard deviations. So we could actually do like, if we did the section that I've eliminated, we would do hypothesis tests about standard deviations. So you guys, I just want to make sure you realize that I've saved you from that. I think you've gone through enough. So you already know how hypothesis tests work. I think I just wanted to focus on how the hell this guy works. Something else this is used for is, well, let me see, I don't want to say this. Let's say that you have, let's say you think you know how grades should be distributed, right? Let me see what you guys think. A, B, C, D, F. So for any given class, what percentage of the class should have A's? 100%, oh yeah. That's what I always hope for, but maybe 10%. All right. What percentage would have B's, do you think? All right, about 25 maybe is the average of everything I heard. Well, how many would have C's? 30 maybe? 30, 40? I'd say 35. What do I have so far? What do I have left here to play with? 30 left. So how many D's you think? What percentage are D's? 20? Man, you guys have been through some rough times. So that leaves me with how much for F? 10%. All right. So that was kind of put together, all together. All right. And this is sort of roughly normal what we've just done there, right? And that's like bell curve, that infamous bell curve of grades. All right. All right. Now, so we have this. This is the expected distribution. Now, what if we actually go and say, I want to check to see if this certain class follows this expected distribution. So this is what's called a goodness of fit test. I love the name. That's the actual name. It's not me. The name of this thing is the goodness of fit. The Goff test. Right? No. Oh, poor little dude. So let's say we go see a specific class. How many students are in this class?
38.
38. Let's say I see 2 A's, 11 B's, 6 C's, 12 D's, 7 F's. Okay. Ooh, that's gross. Well, actually, there was once there was a guy who had a 0.00001. Once one person made it to the final and they failed it. So I'll let you figure that out. It is somebody here. I didn't say your name. So already you can tell it seems to be off from the expected, right? So one way that this distribution can be used is, and again, the normal distribution exists. So we take some distribution from the real world, And then we make z-scores out of it so we compare it to this already known thing that's got all its percentages spelled out on the picture, on the chart for us, right? So if we take, one way to use this chi-square, one formula for it, there are several formulas for chi-square because it's sort of like z-scores. So if I take, let me see, I want to do this the same order that they do it here. Okay, good. Different books do it in different ways. It's squared, so it doesn't really matter, but I just want to do it the same way. Over E. Yeah, cool. I like it.
That first squiggle on the
Well,
top,
it's got to be over everybody.
that's the sum, right? That you just put there?
This is the sum, yeah. All right. All right. Let's just write that down, and we're going to analyze what the hell this is. It sort of feels like the first time we did standard deviation. It's got the summation formula in there. What do you think the E stands for? Expected. So I'm going to have these values kind of like to work with. What do you think the O stands for?
Observed.
Observed. Crazy. I like it. Right? I'm sorry, there's no prizes. Not a game show. So what I need to do now is, I know I need a sum. If I cover the sum formula, I see what I need to calculate. If I get a bunch of these, I can add them up. And that'll be my chi-square score. So right now, we're just going to do that. We still have to look at the chart for chi-square and figure out how the hell it works, so we can get our critical score to see if we find enough evidence. And you're not going to have to do an entire hypothesis test. Don't freak out. But how do I put together this formula? Well, for the expected, I got 38 kids, right? How many A's would I expect in? 10% of 38 is exactly 3.8. So don't worry that you can't get that. That's just your theoretical expected, right? So you'd expect 3.8 A's. How many? Does everybody see that? I expect 10%. Well, then I can handle any size class then. I just take 10% of the size. So 25% of 38. Does everybody go, why did they pick 38? Too bad. I liked it. 9 point something. I don't know.
9.5.
9.5? C's?
13.3.
13.3. Are you guys understanding where those numbers are coming from? 20% of 38.
7.6.
And then 10% of 38. 3.8. Now what are the observed values? Observed. Those are my observations. So you can see here, it makes it a little clearer. That's not too far away. That's not too far away. That's kind of far away though, isn't it? That's pretty far away, and that's twice almost what I expect, right? All right. But still, it's you can't look at values and tell, just like hypothesis tests. They could be really far away, but at the end, the z-score is not big enough. So you can't just look at it and tell. So how am I going to put together this business? Well, I probably want to do... Well, let's see if we can handle that, do that all at once. So you can imagine the lists would help you. They have a long list of data. This isn't that bad. Let me stop there for a second. Now real quick, let me make sure some of this makes sense from like an extreme standpoint. If this matched exactly what I expected, what would each of these be? If this matched exactly what I expected, then this difference would be 0. So these would be 0. 0 divided by e would be 0. So my score would be 0. So a score of 0 means they match exactly. So the whole idea then is going to be this. I got to figure out what value is my cutoff so that if I go beyond that, it's too far away from 0. It's evidence that they're different. If they are the same, it should be close to 0. If they are different, it's going to be far enough away from 0. So the next step after we finish calculating a score is, how do I read the chart to tell what that far enough away is? So, oh crap. I'm going to try to do that in my head. The value of using the calculator lists is you don't have to round anything, but we'll be all right. Are you guys able to get those values? All right, it's nothing major, right? Just divide. Now I can finally do what this wants me to. It wants me to add up all these. So if I add those up, let's see, I get 10.34.
Yeah.
All right. So, one major difference before we start talking about this chart is that z-scores can be positive and negative, right? T-scores can be positive and negative. Chi-square scores cannot. And that square is a part of the symbol. Don't try to square root to get chi by itself. Chi-square is the symbol. Maybe. It's related to where it comes from, but it's just the symbol for this thing. It's like Z star. You can't take the star root of it. Chi-square, the lowest value is 0. And then the other side is unbounded because it looks like this. Whoa. Okay, so it's not symmetric. That kind of sucks. I am not going to be able to say negative 2.326 to 2.326 anymore. That was symmetric. This is not symmetric. And it starts at 0. There's not going to be any negatives. So there's going to be some trade-offs. It's not going to be as quick to find things. So let me give you this chart, and then we got to figure out how the hell to read it. In my head, I could hear you guys describing stats to somebody. It's a bunch of charts and numbers. It's actually not wrong, but it's more than that, hopefully. Now, when you do goodness of fit test, the degrees of freedom is based on the number of categories. So here there's 1, 2, 3, 4, 5 categories. So my degrees of freedom will be 5 minus 1 will be 4. So it's not the total number, it's just the number of categories that I'm looking at. Let me see. Because the categories could be colors of M&Ms. The categories could be blood pressures. The categories could be whatever. And you want to compare the expected values to whatever's happening. So if I find a little group of people and they're all like have excellent blood pressure, and they're way far off from what I would expect, after doing this test I would go, whoa, they're way far off. Let's go see what the hell they're eating. Let's go see what the hell they're doing. And maybe, make a big thing out of this. Write a book. Make some money. Get people in better shape. Alright. So you'll notice one thing I still have to tell you is the level of significance. Now what really kind of sucks here is notice it says area to the right of the critical value. So anytime we're doing a, let me do it up here. Anytime we're doing a goodness of fit test, this thing we're doing right now, good. The whole idea is I want to see it's got to be far enough away from 0. Here's 0. That would mean that they match up perfectly. So I want to set up kind of like the rejection region out here. It's got to be far enough away from 0. So I want to find this chi-square. So if I'm using a level of significance, let's use 0.05 level of significance. Right? That's the alpha. So what area is going to be in the tail? Well, it's going to be that 0.05, right? And see, now be careful. Now the tail, now of course, just to be evil. For the z-score, it's in the left side of the thing. For the chi-square, it's on the right side of the thing. Oh well, too bad. So I'm going to look at 0.05. That's to the right of my critical value, my rejection region value. And then I'm going to go down to degrees of freedom of 4. And I get 9.488. So that's the biggest chi-square it could be. It's the furthest away from 0 that could be, and still